Good morning, students. Am I audible? ಕೇಳಿಸ್ತಾ ಇದೆನಾ?
Yes, ma'am.
Okay. Today we'll discuss functions of single random variable. So here, previously we have seen the expectation operator. So here we have used the expectation operator, which was introduced as y is equal to g of x. So where this g of x, so whatever x, it may be any random variable, maybe y, it may be w, or any random variable. So here, in general, we can say that g of dot, it is some function using y is equal to g of x, we will be able to map some of the observation in Sx into new region. And whatever new mapping will be done, so that will be considered as a new set and denoted as Sy. So here, whatever the expectation operator we have introduced, y is equal to g of x. So here the function g of x, so here using which we will be able to map some of the observation in the sense possible outcomes whenever you'll be performing some experiment. So here for that experiment you will be getting some output, so or in general you can consider that as outcome. So here those outcomes which are present in the set Sx, so they can be mapped into a new region, so which will be taken on the real set denoted as Sy. And here this operator, it can be used in various operations. So for example, we'll be performing amplification. So in AC lab, we'll be executing or performing the amplifier circuit, right? So you'll be implementing the amplifier circuit. So here in such circuit, in order to analyze that, so here we can go for using this expectation operation. And other than that, we can also use it in the case of level shifting, clipping, or in order to find some power. And here usually this whatever y is equal to g of x function will be having, so that will be frequently used in most of the applications in the engineering field. And now the main agenda in this functions of single random variable is, so here we'll try to demonstrate, suppose if we know the original function or the original pdf fx of x. Suppose if we know the original PDF fx of x, and also if we know the function g of dot, that is g of dot is nothing but the function of any random variable. So if we know PDF, original PDF, as well as the function g of dot, then which is used in the case of y is equal to g of x. So in such cases, we will be able to find the PDF of any other random variable. So for example, y. So here we can calculate the PDF of y, which is represented as fy of y, and also we can calculate the associated CDF as well as the new outcomes which are taken in a new set which is represented as Sy. So here the main agenda in studying the function of single random variable is, suppose if you are given a original PDF fx of x for a random variable x, and also if we know the function g of dot, what it will be performing. So in such cases, so here we will be able to find the PDF of some other random variable y, and that is denoted as fy of y. And also suppose if we know the PDF, so here easily we can also calculate the CDF and also the associated outcomes which are taken on the real Sy. So here the process whatever will be used in the functions of the single random variable. So it assumes that, so here we will be knowing the inverse of the function y is equal to g of x. So assuming that we are going to perform all the operations. So here suppose if we consider the function y is equal to g of x. So here the inverse of this function, simply it will be written as what? X is equal to g inverse of y. So here, assuming the inverse function or inverse process is known, so here we are going to identify the PDF, associated CDF, as well as the possible outcomes in the set Sy. So now we are going to assume or we are going to consider some arbitrary random variable x, and also we'll assume that we know the PDF and CDF of the random variable x. So here, in order to analyze this function, we are going to make use of the transformation function that we have studied. So here, as we have seen, so here the transformation function, it is represented as y is equal to ax plus b. So here, where this a, it is considered to be positive constant. So here, keep in mind. So here we are saying that a is a positive constant and b is constant. So otherwise, any constant, it may be positive or negative. So otherwise, it will be considered as any arbitrary constant. So here, as I told, so here in this example, we are going to consider the transformation function y is equal to ax plus b. So here, in the beginning, I told that here we are going to assume that the inverse process of the transformation function will be known. So here we are going to write the inverse function of this equation 1. So here, as we have as we are seeing here, y is equal to ax plus b. So from this, we will be able to write the equation for x. So here x becomes what from this equation? Y minus b divided by a. So where a is assumed to be a positive constant, so here we'll be writing a is greater than 0. And here, whatever the equation that we are going to see here, y is equal to ax plus b. So here for that, suppose if you plot the graph, so it looks like this. So here, whatever this line that you are going to see here, so here this represents the output of y is equal to ax plus b. So from this graph, so here we will be able to identify some of the features. So here, for example, suppose if you are given the value of the independent variable y, so in such cases, we will be able to identify the region along this y axis for which y capital Y, that is the random variable y, is less than or equal to the independent variable value small y. So here you can see that for y less than or equal to y, so here we will be able to identify the region along the y axis. And here, as also we have seen that we have a inverse function x is equal to y minus b by a. So here, whatever the values of y will be given, for example, if you take the value of y is equal to 1, so for the same value of y is equal to 1, so here using the inverse function, so here we'll be able to identify the region along the x-axis where we are going to assume x capital X will be less than or equal to y minus b by a. So here you need to remember these points. So because here we are assuming that a is a positive constant. So in the next example, we'll be considering a as a negative value or negative constant. So for that reason, whatever the symbol or whatever the notations that we'll be using, that matters a lot. So while explaining this concept, you have to remember all this. So here we'll be assuming the function y is equal to ax plus b is known to us, and for the given transformation function, we are going to assume we'll be knowing the inverse process x is equal to y minus b divided by a. So assuming that, so here suppose if you given the value of the independent variable y, so we will be able to identify the region along the y axis for y less than or equal to independent variable y. So here we'll see what will be the values of independent variable with the suitable example. And for the same value of y, you should be, we will be able to identify the region along the x-axis for which we are going to assume x is less than or equal to y minus b by a. And also here, whatever the equation 1 and 2 we have seen, that is y is equal to ax plus b and x is equal to y minus b by a. So these two functions will help us to connect the random variable x and y. So here we can write, so fy of y, that is the CDF of the random variable y, it is simply written as probability of y less than or equal to y, which is also equal to probability of x less than or equal to x. So here, which implies that probability of x less than y minus b by a. And here using this, whatever the probability we are going to see on the right side. So this is nothing but the CDF of the random variable x with the independent value y minus b by a. So here we'll be able to write fy of y is equal to fx of y minus b by a. So this is the relationship that exists between the random variable x as well as the y. And this equation number 3, it is called as the conservation of probability principle. And here using the equation 3, so we can also find the PDF. So here we know that PDF and CDF, they are interrelated to with each other. So here we can find the PDF given the CDF. How we are going to calculate? So here with the help of the CDF, suppose if you differentiate that CDF, we will be getting the PDF. So here we can use the equation number 3, and here we can take the differentiation of Fy of y. So here we can write small Fy of y is equal to, there is nothing but the PDF on the left hand side, which is equal to differentiation of Fy of y with respect to x. So here on the right hand side, you are going to see the equation for Fy of y. So here Fy of y is replaced as Fx of y minus b by a. So here you are going to substitute the right hand side value in the differential term. So here we'll be getting Fy of y is equal to d by dx of Fx of y minus b by a. So that has to be differentiated with respect to x. So here we'll be getting Fy of y is equal to, so here the differentiation of this will be 1 by a into Fx of y minus b divided by a. So where a is greater than 0. So that is the equation for the PDF. So this is one example which shows the mapping of one variable into another variable. And similarly, we can take one more example. So here we are going to make use of the transformation function y is equal to sigma y x plus mu y. So here this equation, it was obtained assuming that the mu x of the random variable x is equal to 0 and the variance sigma x square is equal to 1. So assuming mean is equal to 0 and variance is equal to 1. So we have obtained this equation. So for that, you can go to the page number 28. So here whatever the notes I have given, so in that, so here this derivation has been given and also explained in the class. So here suppose if we consider a random variable x which with a mean of 0 and a variance is equal to 1, so then we will be getting mu y is equal to b as well as sigma y is equal to a. So here for the transformation function y is equal to ax plus b, so we got y is equal to sigma y x plus mu y. So here the same equation which was obtained here, so that can be applied, to the Gaussian random variable z. So here the Gaussian random variable z, it can be related to the random variable x by the relation x is equal to sigma x z plus mu x. So here for this equation also, we are going to assume that the mean of the random variable z is equal to 0 and the variance of the random variable z sigma z square is equal to 1. So here for this Gaussian random variable z, so we can connect the variable y and x. So using the equation Fy of y is equal to Fx of y minus b by a. So here this equation we have seen. So here using the similar equation, so we can connect x and z. So here we can write using the same equation. So this is rewritten as Fx of x is equal to Fz of, so here y represents what? So here we can see the equation. So x is equal to sigma xz plus mu x. So here from this we will be able to identify the values of a and b. So here since we are using the variable x, or mu x is, just a minute. So fz of x minus mu x divided by sigma x. So here b is nothing but the mu x value as well as a is nothing but the sigma x. So here we will be able to write fx of x is equal to fz of x minus mu x divided by sigma x. So which can be for the Gaussian variable, we have seen that it will be useful if we represent in terms of the notation phi. So here instead of fz, so here it will be written as phi of x minus mu x divided by sigma x. And where this whatever phi of z, so here this will be generally taken as z is equal to x minus mu x divided by sigma x. So here this phi of z, it represents the CDF of the normalized Gaussian random variable. And as we know, the Gaussian PDF fx of x, it is obtained by taking the differentiation of fz of x minus mu x divided by sigma x. So here that will result in fx of x is equal to, so here the differentiation of this with respect to x is 1 by sigma x into fz, small fz of x minus mu x divided by sigma x. And as we know that, so 1 by sigma x will be there, 1 by sigma x will be taken this side, and fz of x minus mu x divided by sigma x, this is nothing but the PDF of the random variable z. And as you, and as we know that for the random Gaussian random variable z, the PDF, for example, if you consider this as fz of z, so here we used to write the PDF as 1 by root 2 pi e to the power minus z square by 2. So here, since z takes the value x minus mu x divided by sigma x, so here we are going to write the PDF fz of x minus sigma mu x divided by sigma x as 1 by root 2 pi e to the power minus, in place of z square, we will be replacing that as x minus mu x whole square divided by sigma x square. And anyhow, z square by 2 was there. So here we'll be introducing 2 at the denominator. So here we can write fx of x is equal to 1 by root 2 pi sigma x e to the power minus of x minus mu x whole square divided by 2 sigma x square. So this is the PDF for the given transformation function. And for this, this has been shown, the PDF and the corresponding CDF plots have been shown. So here this has been drawn assuming that the mean mu x as 1000 as well as the standard deviation sigma x as 50. So here assuming those values, this is the plot that is being obtained. So you have to remember these plots and just plot it. And so suppose whatever the plots that is been shown, so it is drawn for about the mean value. So here it will, the whatever the PDF you are going to see, so this PDF, it is going to take the peak value about its mean value. So here the value of the PDF is maximum about its mean. So here whenever you assume x becomes mu x, so here x mu x minus mu x becomes 0, e to the power 0 is 1. So at that time only you will be getting the PDF value as maximum. So here you need to mention this point also. So here the PDF of the Gaussian random variable with the given transformation, it will have its peak value about its mean value. And also here, suppose if the standard deviation sigma x is relatively small, then the PDF at its mean is going to be relatively large. That is, the reverse connection will exist between the standard deviation as well as the PDF. So yes, if suppose if the standard deviation sigma x is small, then the PDF about its mean value, it is going to be relatively large, and the vice versa, that you can explain it. And next here we are going to take one more example. So here we are going to consider an example. I just read out the example that is been given. A production drawing specifies a dimension on a printed circuit board as 0.75 plus or minus 0.002 centimeter. Assume that the process that manufacturer manufactures the devices is such that the dimension is a Gaussian random variable y, and that the manufacturing process is accurate, that is mu y is equal to 0.75, and assume that the precision of the manufacturing process is such that the standard deviation is sigma y is equal to 0.0013 centimeter. And here given all these parameters, so here we will be interested to find the percent of the printed circuit boards having the dimension within the specified tolerance limits from 0.748 centimeter to 0.752 centimeters. So that we'll see how to calculate the percentage of tolerance limits. So here in the beginning you can see that it has been given with the dimension, whatever the printed circuit we have, so that is given with the dimension 0.75 plus or minus 0.002 centimeter. So here from this 0.75 minus 0.002 ಮಾಡಿದ್ರೆ ನಿಮಗೆ you will be getting 0.748, and 0.75 plus 0.002 ಮಾಡಿದ್ರೆ you will be getting 0.752 centimeter. So here that is nothing but the specified tolerance limit which is obtained from this given specification. So that's why they have mentioned 0.748 centimeter to 0.752 centimeter. Along with this dimension, they have also given mu y value as 0.75 centimeter and sigma y value as 0.0013 centimeter. So given this parameter, so here will be asked to calculate the percent of printed circuit boards. So here having the given dimension. So here we can write probability of 0.748 less than y less than 0.752. So here we are taking the independent variable y. So here independent variable y. So as I told in the beginning of the topic, so here we'll see how to see the how to take the values for the independent random variable. So this is a, so here this is this independent random variable, the values will keep varying. So here for this example, the dimension itself represents the independent variable values. So here for that, and also is specified that it is a Gaussian random variable y. So here for that reason we are mentioning probability of 0.748 minus y less than 0.752. So for this, we need to calculate the percent of the printed circuit boards with the given dimension. So how we are going to calculate? We have seen this method earlier, right? So if this represents y2 value and this represents y1 value. So here we can write fy of 0.752 minus fy of 0.748. So now, as I told for the Gaussian, so instead of solving this, so usually we go for tabulating the values from the appendix. So here we are going to make use of the appendix values. So here Fi of 0.752, it can be written as phi of, so whatever the formula we have given here. So here, this is the formula. It is that x minus mu x divided by sigma x. So here that represents the z value. So here using that, so here we'll be able to write that phi of 0.752 minus 0.750. This 0.750 is nothing but the mean value. So here you can see that mu y is given as 0.75. So don't mix this 0.75 with this 0.75. So the whatever we are substituting here, so that represents the mean value. So here phi of 0.752 minus 0.75 divided by sigma x. So sigma is nothing but here 0.0013 for the given random variable y, minus similarly phi of 0.748 minus 0.75 divided by 0.0013. So here whatever the bracket terms we have, so that is going to be simplified and that will be written here. So here we'll be getting in the next step as phi of 1.5385 minus phi of minus 1.5385. And we have seen how to tabulate these values for the positive values of z as well as for the negative values of z. So here instead of z, we are given with the value of y. So here the same table will be used. So here we are going to make use of the interpolation method. So use the interpolation method and get the value for both. So while solving the problems, we'll see how to do that once again. So here by the interpolation method, these are the values that is going to obtain. So which will give the value as 0.876, and in terms of percentage, so that will be obtained as 87.6%. So here whatever 87.6% we have obtained, so this represents the manufactured printed circuit board. So these those many boards they come under within the desired specification, and the remaining 12.4% of the boards, so they will be either less than that or they may be more than that. And similarly, we are going to consider one more transformation function which is defined by y is equal to ax plus b. Whatever the first example we have seen, the same example is going to be taken here. Only the thing is here we are going to assume that a is a negative constant and the inverse function remains same. So but here a takes the value less than 0. So that's why I told. So here suppose if you are explaining for a as positive constant, so that will be the different case, and here we are going to assume a as negative constant. So here for this the inverse function remains same, only the thing is a will be less than 0. So for this whenever a is negative constant, so here the slope it will be reverse. So here it will be like this. So here from this also So suppose if you are given the value of y, so here we will be able to identify the region along the y axis. So for y less than or equal to y, and for the same values of y, so here we will be able to identify the region along the x axis. But here we have to see that, so here for x it will be greater than or equal to y minus b by a, as slope is negative. So for positive slope a positive, so here we'll be considering a x less than y minus b by a. But here since a is negative, that is the slope is negative, so here we'll be able to identify the region along the x axis for x greater than or equal to y minus b by a. And here using these two key features, we are going to connect random variable x and y. So with the equation fy of y is equal to probability of y less than or equal to y, so which is also equal to probability of x greater than or equal to y minus b by a. So you cannot write x less than y minus b by a. So here we need to write probability of x greater than or equal to y minus b by a. So which is equal to 1 minus p of x less than y minus b by a. So here that will be equal to fy of y is equal to 1 minus. So this probability of x less than y minus b by a, it represents the CDF fx of y minus b by a. And the corresponding PDF is obtained by taking the differentiation of this. So here that will be represented as fy of y is equal to fx of small fx of y minus b by a into 1 by a you will be getting, but with the negative sign. So as the equation itself shows that a is less than 0. And here one more example. So here we are going to consider the function y is equal to a x square, where a is greater than 0. So y is equal to a x square, as we know that this is nothing but the equation of the parabola. So here you can see whenever you are going to plot this, you are going to get the graph like this, right? For y is equal to a x square, where a is assumed to be a positive constant, or a is greater than 0. So here for this function y is equal to ax square, the inverse function, it can be written as x is equal to plus or minus square root of y by a. So here as you can see, x square it is written as y by a, which implies that x is equal to plus or minus square root of y by a, where a is greater than 0 as well as y is greater than 0. So for this also, when you are going to plot this, so here for the given value of y, so we'll be able to identify the region along the y-axis for y less than or equal to y, and also for the same values of y. So we'll be able to identify the region along the x-axis. So for x between minus root of y by a up to x is equal to plus root of y by a. And one more thing you need to explain. So for the negative values of y, so we will not be able to map the observations. So because whatever the parabola that you are going to get for the equation y is equal to ax square, that is only above the positive y-axis. So for that reason, we will not be getting any observations for negative values of y. So that you need to explain. So for this example, we can connect the random variable x and y using the equation fy of y is equal to probability of y less than or equal to y. And as I told, so this y less than or equal to y, this is also equal to probability of minus square root of y by a less than or equal to x less than or equal to plus of square root of y by a. So this is nothing but the region along the x-axis. So here within this range, we will be able to identify the probability. So for this, we can write in terms of the CDF as fx of square root of y by a minus fx of minus of square root of y by a. So here this is y2, this is y1. So using that, we'll be able to write the PDF, CDF equation. And the corresponding PDF, it can be obtained by taking the differentiation of this equation. So this takes somewhat 2 to 3 steps, so that you can go here. So fy of I is equal to differentiation of fx of square root of y by a minus fx of minus square root of y by a. So steps are being shown here. You just go with all these steps. So finally, we'll be getting the answer as 1 by 2 square root of ay within the flower bracket fx of square root of y by a plus fx of minus root of y by a. So these are some of the functions which are related with the single random variable. So other than that, we'll also have some computer simulations. So here computer simulations, they will be used in order to analyze many engineering problems and also engineering designs. So here the main concept in the computer simulation is, so here we should be able to identify the algorithms which will be producing a reverse or reverse process whatever we have seen manually. So in the above example we have seen the reverse process manually. So here what here in this, whenever you'll be going with the computer simulations, we will be able to identify the algorithm which will be able to produce the reverse process. So for this, the one example is been shown, and you just go with this. This is very simple concept. And whatever y is equal to g of x is equal to fy inverse of x, we have taken the same equation. And for this we have taken one example. So here we'll see, with this example we'll see how to identify the algorithm. So here suppose that if you want an algorithm to simulate observations of an experimental or exponential random variable y with the parameter and as we know that for the exponential random variable, the CDF is given as Fy of y is equal to 1 minus e to the power minus lambda y for y greater than or equal to 0, and it takes the value 0 for y less than 0. So here uh, we will be reducing this to the term Fy of y is equal to 1 minus e to the power minus lambda y, which is simply taken as x. That is from the equation y is equal to g of x is equal to Fy inverse of x we have taken. So from that we'll be writing this and we'll assume that it will be lying between 0 to 1. And as we know, y is equal to g of x is equal to Fy inverse of x. So you're using the inverse function. So and solving for y, we will be getting the answer or whatever the algorithm that we'll be looking into. So here from this we can write x is equal to 1 minus e to the power minus lambda y. So you just rearrange the terms. E to the power minus lambda y, it will be taken onto the LHS, and x which is present on the LHS, it will be bring onto the RHS. So here we'll be getting is equal to 1 minus x. So here now for this we are going to take the logarithm on both sides. So taking the logarithm on both sides, so here we can get ln of e to the power minus lambda y is equal to ln of 1 minus x. So here ln of e to the power minus lambda y, it can be written as minus lambda y ln e is equal to ln of 1 minus x. And here as we know, ln e to the base e is nothing but 1. So here we are going to replace it by 1. So here we'll be reduced with minus lambda y is equal to ln of 1 minus x, which implies that y is equal to minus 1 by lambda ln of 1 minus x. So here this is the required reverse process that can be obtained for the given exponential random variable. So here on this, we are going to solve some of the problems, and also we'll see how to get the answer. And the next topic is conditioned random variable that we are going to look in the next class. Thank you.